Time travel. For decades, we've been told it's impossible. A fantasy relegated to science fiction movies and comic books, something that violates the fundamental laws of physics. It's just not possible. That's what every physics textbook will tell you. But here's the thing. Some of the most brilliant physicists in the world, the people who actually understand the universe better than anyone else, disagree. They're not cranks or conspiracy theorists. They're serious scientists who work at prestigious universities, and they've spent their entire careers examining the mathematics of time itself. They found something deeply troubling in Einstein's equations, something that shouldn't be possible according to conventional wisdom. They found solutions that allow time travel. And that raises a question nobody wants to ask. If the math works, if the equations don't technically forbid it, then why are we so certain it can't happen? Why do we dismiss it so quickly? Is it because we've found a fundamental reason it's impossible? Or is it simply because we're uncomfortable with the idea? Because the closer you look at the actual science, the less clear the answer becomes. The reality is far stranger and far more complicated than most people realize. Think about it. We tell children that time travel is impossible, that it's the realm of fantasy, but we don't teach them why it's impossible. We just assert it as fact. And that's revealing. Because most people, including educated people, can't actually explain the fundamental physics preventing time travel. They just accept that it's impossible because they've been told it's impossible. But physicists aren't so certain. They understand that the universe is far more flexible than our everyday experience suggests. Time isn't the rigid, unchanging thing we perceive in our daily lives. It's malleable. It's bendable. It responds to gravity and velocity and the distribution of mass and energy throughout space. If you understand this, really understand it, then the idea that time travel might be possible doesn't seem quite so absurd. In fact, it starts to seem almost inevitable that someone, someday, might figure out how to do it. For centuries, time seemed like an absolute, an unchanging constant that flows at the same rate for everyone, everywhere. Newton believed this. Most scientists believed this. Time was this universal background, independent of anything else, completely separate from space. But then, in 1905, Einstein showed us something remarkable. Time isn't absolute. It's not independent. Time is woven together with space itself, part of something called space-time. And here's what makes this radical. Time can speed up and slow down, depending on where you are and how fast you're moving. Einstein called this relativity, and it fundamentally changed everything we thought we knew about how the universe works. But most people don't really understand what this means. They hear time is relative, and they think it's just a theoretical abstraction, something that doesn't matter in the real world. But it does matter. It's real. We've measured it. Consider this. If you travel in a super-fast spacecraft, moving at close to the speed of light, time actually moves slower for you than it does for people on Earth. This isn't metaphorical. This isn't philosophical. This is measurable, testable, proven. We've confirmed this with atomic clocks on airplanes, on satellites orbiting Earth. The astronauts on the International Space Station age slightly slower than people on the ground. Not by much. We're talking fractions of a second over months of being in orbit, but it's real. It's called time dilation, and it's a direct consequence of Einstein's special relativity. If you could somehow travel at 99% the speed of light, traveling away from Earth and back, you might experience only a few years passing while a century passes on Earth. You would, technically, have travelled into Earth's future. You wouldn't feel like you time travelled, but from Earth's perspective, you did. You skipped ahead. You missed decades of Earth's history. This is time travel. It's not the Hollywood version, you're not going backward, but it's genuine time travel nonetheless. The math is even stranger when you consider gravity. Einstein's general relativity tells us that massive objects warp space-time around them. A spinning neutron star, or a black hole, or even Earth itself, creates a dip in space-time, like a bowling ball on a trampoline. Time moves slower closer to that massive object. So if you could somehow live on the surface of a neutron star near its intense gravity, time would move dramatically slower for you compared to someone far out in space. You might experience 1 year while 1,000 years pass elsewhere in the universe. Again, from your perspective, nothing unusual happens. You live your normal life, but everyone else sees you moving in slow motion, aging incredibly slowly, effectively traveling into their future. We've observed this effect, we've measured it, we know it's real, but here's where it gets strange. Most people think of time travel as going backward, going into the past. Going forward is acceptable. We already do that at incredibly tiny scales. But going backward, that's where physics gets weird. That's where everyone says it's impossible. But if you look at Einstein's general relativity equations, the ones that describe gravity and how massive objects bend space and time around them, you find something unexpected. You find solutions that allow closed time-like curves. That's physicists speak for a path through space-time that loops back on itself, allowing someone to theoretically return to their own past. Einstein himself didn't like this. He called it one of his greatest embarrassments, but the math doesn't lie. The math allows it. Now, we know what you're thinking. Okay, so the math allows it, but that doesn't mean it's actually possible in the real universe. We have to distinguish between mathematical possibility and physical reality, right? That's true. But here's what's troubling. Physicists have found several potential mechanisms that might make this work. Black holes, for instance. When a massive star collapses at the end of its life, it can form a black hole, a region of space-time so warped, so dense, that not even light can escape. We know black holes are real. We've observed them. We've photographed them. Inside a black hole, space-time becomes so distorted that the normal rules break down. And some physicists have suggested that if you could somehow navigate through certain types of rotating black holes, or through wormholes connecting different parts of space-time, you might emerge in the past. The equations allow it, but we've never tested it. We've never observed it. We don't know if the universe actually permits this, or if there's some deeper principle we haven't discovered yet that prevents it. Then there's the wormhole possibility. A wormhole, in theory, is a shortcut through space-time. Imagine taking a sheet of paper and folding it so that two distant points touch. You could travel between them instantly, or nearly so. General relativity allows wormholes to exist, at least mathematically. But here's the problem. To keep a wormhole open, you would need something called exotic matter, matter with negative energy or negative mass. We've never directly detected exotic matter. We don't know if it exists in usable quantities. Some physicists have suggested that dark energy might be exotic matter, but that's highly speculative. So even if wormholes are mathematically possible, they might be practically impossible. You might need technology we'll never have, using materials that don't exist in sufficient quantities anywhere in the universe. Now you might ask, what's exotic matter anyway? Why would you need something with negative energy? Well, here's the deal. A wormhole, if it's to remain open, needs to have what's called negative curvature. It needs to counteract the gravitational attraction that would normally collapse it. Imagine a rope on the edge of a cliff. Gravity pulls it down. To keep it from falling, you'd need something pulling it up. That's what exotic matter does. It pushes rather than pulls. It repels gravity. And yes, theoretically, we know that negative energy might exist in the quantum vacuum, the seething foam of particle-antiparticle pairs that physicists believe fills all of space. The Casimir effect, observed in labs, hints that negative energy densities might be achievable using quantum field effects, but we're talking about needing enormous quantities of it, perhaps the mass energy equivalent of entire planets, maintained with perfect precision. That's not happening anytime soon. But this is where it gets really interesting. Physicists have discovered something even stranger in recent years. They've found that certain solutions to Einstein's equations predict not just wormholes, but rotating Kerr black holes that might contain traversable passages through time and space. A regular black hole, a non-rotating one, would crush anything that fell into it. The tidal forces would be lethal, but a rotating black hole is different. The spin creates a region, called the ergosphere, where space-time itself is dragged around by the black hole's rotation. Some theoretical models suggest that you could pass through the inner event horizon of a rotating black hole without being destroyed. You might emerge in a different part of the universe, or in a different era of time, or potentially even in a parallel universe. The mathematics is complex, but it allows for these possibilities. And some researchers, using quantum field theory calculations, have found that what looks like exotic matter might actually be producible using quantum effects at extremely small scales. We're talking theoretical possibilities here, but they're not laughed out of rooms anymore. They're being taken seriously. They're being published in peer-reviewed journals. The idea that time travel might be possible has gone from science fiction to serious theoretical physics. This is remarkable when you think about it, because just decades ago, suggesting time travel was theoretically possible would get you laughed out of a department. Now it's mainstream research. Universities hire physicists specifically to work on these problems. Of course, there's a massive problem, the grandfather paradox. If you travel back in time and kill your grandfather before your parent was born, then you were never born, which means you couldn't have traveled back in time to kill him. But then he's alive, so you would be born and you could travel back. It's a logical contradiction that most people assume proves time travel is impossible. It must be impossible because allowing it creates paradoxes. But here's what's fascinating. Physicists have found ways around this. Several ways, actually. One solution is the many worlds interpretation. Maybe when you travel back in time, you create an alternate timeline. You don't erase your own history. You create a parallel universe. So you go back and kill your grandfather, but it's an alternate universe's grandfather, not yours. You still exist. The paradox is avoided. There's no contradiction. This interpretation is based on quantum mechanics, the idea that reality constantly branches into multiple parallel possibilities. Every choice, every quantum event spawns new universes where different outcomes occur. If this is true, then traveling backward through time wouldn't erase your past. It would just send you to an alternate reality where things were different. Another solution is something called the chronology protection conjecture, proposed by physicist Stephen Hawking. Hawking suggested that the universe might have some built-in protection mechanism that prevents paradoxes. Maybe closed time-like curves can only exist in ways that are self-consistent. If you go back in time to kill your grandfather, your gun will jam, or you'll miss, or you'll discover you're not actually his grandchild. The universe, in some sense, would prevent the paradox from occurring, not through some external force, but through the constraints of what's already happened. The past is fixed, immutable. You can't change it because it's already there. You can only be part of it. If you went back in time, you were always there. You already tried to kill your grandfather and failed. You were always meant to fail. This solution, strangely enough, doesn't make time travel impossible. It just makes it complicated. It means you couldn't change the past, but you could potentially visit it. You could be a witness to history, but not alter it. Or alternatively, the many worlds interpretation might apply, and you could change an alternate timeline. Either way, the fundamental contradiction that everyone says proves time travel is impossible might not actually be a deal breaker. Physicists have thought through these paradoxes, and they've found that logical consistency can be maintained even if time travel is possible. The universe might be stranger and more flexible than our intuitions suggest. These aren't wild speculations. These are serious solutions proposed by serious physicists at major universities, published in peer-reviewed journals. But let's be clear about what we actually know versus what we speculate. We know that time is relative. We know time dilation is real. We know Einstein's equations allow mathematical solutions that predict closed time-like curves. We know black holes are real. We know wormholes are mathematically possible. But do we know that any of this adds up to actual practical time travel? No, we don't. No one has built a time machine. No one has observed anyone coming back from the future. Our current technology is nowhere near capable of manipulating space-time in the ways required. If you wanted to create a wormhole, you'd need to manipulate the fabric of space-time itself, bending it in ways that require energy far exceeding anything our civilization can produce. We're talking about the energy of stars or black holes, focused with incredible precision that might be forever beyond our reach. Consider the scale of what would be needed. A naturally occurring wormhole large enough for humans to traverse would require the manipulation of massive amounts of exotic matter. We're not talking about small-scale quantum effects that might be generated in a laboratory. We're talking about planetary-scale engineering. Some physicists have calculated that you'd need exotic matter with a mass energy equivalent to Jupiter, carefully arranged and maintained in a specific configuration. That's not just currently impossible, it might be a fundamental impossibility. The universe might have built-in limitations that prevent us from ever accumulating enough exotic matter to make a traversable wormhole. And if that's the case, then even if the mathematics allows time travel, practical time travel will never happen. And then there's the problem of Hawking radiation and vacuum decay. Stephen Hawking discovered that black holes actually emit radiation and slowly evaporate over time. This poses a problem for black hole-based time travel because your black hole might disappear before you finish your journey. The intense quantum effects near the event horizon, the boundary of a black hole, cause virtual particle-antiparticle pairs to sometimes separate. One falls into the black hole while the other escapes, carrying away energy. Over eons, this process causes the black hole to shrink and eventually explode. If you were trying to use a wormhole through a black hole as your time machine, you'd better be quick, because it might collapse on you. And some physicists have suggested that trying to manipulate spacetime in extreme ways might trigger vacuum decay, basically a phase transition in the quantum fields that pervade space, converting our stable universe into a different, lower energy state. That would be catastrophic. It might not just destroy your time machine, it might destroy everything. Imagine if opening a wormhole caused a bubble of alternate quantum reality to expand outward at the speed of light, converting all matter and energy into a different form. That would be the end of everything. Not just on Earth, but potentially spreading throughout the entire universe. These aren't certainties, but they're serious considerations that physicists worry about. The point is that even if time travel is theoretically possible, emptying it might destroy the universe, and that's a pretty significant practical limitation. So where does this leave us? The answer is genuinely uncertain. Time travel might be possible. The math doesn't forbid it. But the practical challenges are enormous, possibly insurmountable. We might be living in a universe where time travel is theoretically possible, but practically impossible, forever locked away behind barriers of physics we can't overcome. Or we might be missing something entirely, some deeper principle that absolutely forbids time travel, something we haven't discovered yet. Physics has a way of surprising us. Every time we think we understand the universe, we find something new that overturns our assumptions. Quantum mechanics overturned classical mechanics. Relativity overturned Newtonian physics. Maybe there's something waiting out there, some fundamental law we haven't discovered yet that says time travel is impossible. And in 100 years, physicists will be teaching that as obvious fact. Or maybe, just maybe, someone will figure out how to do it. And our understanding of history, causality, and the nature of time itself will be transformed forever. The honest answer is that we don't know, and that's what makes it so fascinating. The truth is, we should approach this with humility. 50 years ago, gravitational waves seemed like they would never be detectable. They were too subtle. The math predicted them, but detecting them seemed impossible. And yet in 2015, advanced laser technology allowed us to finally observe gravitational waves from colliding black holes. What seems impossible today might become routine tomorrow. What we think is beyond our technological grasp might become achievable with breakthroughs we haven't anticipated. The history of science is full of examples where the impossible became inevitable once we developed the right tools and understanding. So perhaps time travel is the same. Perhaps it will remain permanently beyond our reach. Or perhaps in some distant future, we'll look back on this era and wonder how we could have been so certain it was impossible when the answer was right there in Einstein's equations all along, waiting for someone brave enough to try. So let me know what you think about this in the comments below. Is time travel possible, or will it always be just beyond our reach? For more mind-bending science mysteries and explorations of the universe's deepest questions, be sure to subscribe and join us as we continue uncovering the secrets of reality. Thanks for watching, and as always, until next time, stay curious.